refining it. There's a lot of work in this mobility consortium looking at many of these individual pieces. For example, eco-driving, exactly how much can be saved by more cautious approaches to intersections, managed intersections, energy speed control based on drivetrain management. These things are all studied, and the ranges I'm showing here, for example, eco-driving can save 5 to 15%, I think it shows. And those are getting increasingly solid. There are other important factors. There's a current greater awareness of the importance of the load of sensors and computers on these automated vehicles. And it's not trivial. At one time we thought maybe it could be sort of engineered away through the usual success of electronics progress. But right now there's a consciousness that that load at low speeds can be more than 20% of the energy use of the car. We talked, right sizing was mentioned by Amitai, really important. If we can get the right cars dispatched to the person for the trip, substantial savings. Platooning is when vehicles entrain one another, and that's intensively studied both for trucks and cars. The gains have to do with the length of the trains, the gaps between them, and so there you can save anywhere from 5 to up to 20% for a long train of vehicles. So those are examples of things which can save energy. Things which can cost us energy are higher highway speeds. If automated vehicles are by design and by primary motivation meant to be safe and convenient, and if they're safe, then we could travel substantially faster. And this estimate is simply an estimate of how much more energy we would use if cars would routinely travel on highways at Autobahn type speeds. On the down part of this chart are demand effects. I'm spending a lot of time on this chart because it drives the future results, and I hope some of it's interesting to you. But the identified demand side effects are the introduction of new user groups who might take advantage of an automated traveling service who otherwise couldn't drive, the elderly or other people otherwise incapable of driving. The effects on travel demand of ride-hailing services, and I'll talk a little bit more about the estimates of those ranges of those effects. And then this induced demand, back to the question of cost. If we're providing travel for a substantially lower full generalized cost, we expect, based on the wealth of historical experience, both a short run and a possibly significant long run demand response, induced demand response. So, as I've said, the cost of travel time is really critical, and it's a deep subject. Very interesting to me, this has been studied for years, and the value of travel time savings is actually the principal value that's used in most highway infrastructure investments. That's how they determine whether to add a lane or to add some new road. And so there's a lot of work done, and we see the value of travel time as heterogeneous, depends on the work, whether you're traveling for work or whether you're commuting or leisure, whether it's peak travel or off-peak. And here I give some of the ratios of the estimates of the travel time cost relative to the base cost, which is we'd call 1, typically on the order of half of the wages which are usually used. Now people are working very hard to understand how automated vehicles can alter the cost of travel time. Initial work is with stated preferences, which have all the usual shortcomings. There's more recently some revealed preference work looking at people's choices between ride services and other modes, or using proxy modes, a train being a closer to automated vehicle than a car. A colleague is working with me at the University of Washington on a study looking at people's choices in a single app between driving a car through a car driving service, car sharing service, or taking a Lyft, given all the information about the trip, duration, delays, cost, and you can use that to say how much will people pay not to drive. And we're finding that there's a fair amount of evidence that the cost reduction could well be 20 to 75%, dependent on the type of trip, depending on whether the trip is congested or not. There'd be a higher cost reduction. So these kinds of things need to be understood, and we're working on that. But right now we have some good ranges that we can use for simulations. I said I would talk a little bit more about shared mobility. Maybe many people here are greater experts in this area, and I know some people are greater experts for sure than I am. But there's a wealth of studies showing that at least the current shared mobility system leads to a significant increase in vehicle miles traveled. And so this lists some of the studies ranging anywhere from 30 to 45 and even 60%. Now, of course, the current system is nowhere near optimized, and there's excess riders. But even studies of optimized systems like Loeb et al., with a single provider and optimizing the number of vehicles that are essentially dispatched in an efficient way, still you get 20% increased vehicle miles traveled for basically repositioning the vehicles and picking people up, heading to pick them up and leaving after dropping off. And the other way around this is with increasing pooled riding, which has some consumer disutility that needs to be understood further. It's also interesting, at least parenthetically, that shared vehicles can dramatically reduce the number of vehicles that are needed. So estimates here are that to provide a given set of rides in different urban areas, here's a range of studies, depending on whether pooling occurs or not, these shared vehicles can replace anywhere from 3 to more than 12 conventional vehicles. That doesn't mean there's fewer vehicles on the road, it just means that there are fewer in the stock, and that doesn't mean there's less VMT. But it does mean these vehicles are intensively used, and that, ties into this question that Amitai raised about whether electrification is indeed a preferred strategy for shared automated mobility. And there, Amitai made the arguments for it. High capital cost, low operating cost for electrification fit well with high utilized vehicles. But it's also true that shared companies are interested in profit maximization, and they also can ill afford to take the vehicle out of service, so there has to be very convenient and rapid recharging. I would just notice that it's not guaranteed that electric vehicles will be cheaper than a conventional vehicle. For example, DC, just back of the envelope I did while Amitai was talking, DC fast charging is 30 to 40% kilowatt hour, which is roughly 8 to 12 cents per mile. If you have a 40 mile per gallon hybrid vehicle, that's break even of $3.20 to $4.80 a gallon. And if you read the New York Times this weekend about the amount of oil that's being produced and prospects for future oil prices, that there's still a significant question to be resolved as to whether electric vehicles will dominate, even in this sector where they seem the most effective. Okay, so let me just show you some of the results. So we tied these many factors together and ran a set of scenarios, and these are 2 from the Department of Energy. And we basically saw the kind of result that you may have seen elsewhere, and that is if you have aggressive technology progress, and here we actually have up to 39% battery electric vehicles in both of these scenarios. So there's a lot of base technology advancement as well as some of the other efficiency savings from automation. So you get these orange bars, which are big reductions in the energy intensity of the vehicles. But at the same time, depending on your assumptions about the amount of shared mobility and the efficiency of the number of empty miles traveled, and depending on the elasticity of response to these cost reductions in travel that are quite significant, you see that almost all of our studies showed large responses in vehicle miles traveled. And even in this relatively optimistic case, these are high technology cases, they're called A high and B high. I've got the more details. But one of them the green bar shows that the one on the left is slightly better in terms of energy after it all, and the one on the right is slightly worse. And that's with a very aggressive technology advancement. So that's a challenge, and there's many uncertainties, and so there's a separate process going where we're taking these many factors and interacting them more exhaustively and decomposing them further. So this is early work by Dave Golke and others. And here it's essentially the same picture where the left distribution is the energy intensity effect. The black bar is the no change. And the blue on the right is the vehicle miles traveled, and it varies depending on the cost and the responsiveness to costs. And then the green distribution in the middle is the net effect on energy use. And so this highlights both the significant uncertainty, but still that for most of our expectations, there will be greater energy used. And so the key will be electrification and whether we can get shared mobility. The last example I want to show, so those were aggregate analyses. There's also intensive work going on in spatial analysis, like Amitai showed, called mesoscale studies with explicit road networks in known cities. And this is Bloomington, Illinois, a study done by Argonne National Lab, Josh Auld. And it's a little tricky to read, but I'll just guide you through it. It's the same story where we're looking at different scenarios, only here there's different levels of automation. So take the lower left. This is the change in fuel use due to an introduction of advanced mobility. And so the green and the blue show substantial declines in fuel use due to technological progress. These are efficient drivetrains. And due to lower levels of automation, which provide things like platooning and eco-driving, but don't really reduce the travel cost much, so it doesn't induce a lot of travel. But once you add high levels of automation, full driverless vehicles, there's a large uncertainty, but that's the red triangle, and it shows that for the range of parameters we use, you could essentially nearly completely swamp the gains in energy use. Even, as it shows to the right, even though there's a fair amount of electrification going on. And you can see on the upper left chart that under the case of advanced automation, there's a significant growth of 60 to 80% in vehicle miles traveled. So it's a totally different analytical method, although some of the parameter assumptions were similar result. So this chart is one of those, well, I guess you can't see it, and I apologize for that. But the message is, so we're now looking at, there's a wide range of uncertainty, and the system is likely to respond to economic incentives. And so it really is time to think about strategies and incentives. And here we're looking at what if the cost of fuel were different in the upper left chart, and then what if the cost per mile of road travel were increased. And those, at least in this framework, are strategies for reducing the vehicle miles traveled and reining in energy use. Okay, and I think I maybe have one more slide. The other very important strategy that's being considered, and I don't have a result here for you, but I'm working on now, is incentives for increasing ridership in vehicles. So we're looking at something called a occupancy standard for TNC vehicles, essentially a tradable credit system whereby those vehicles who have run high occupancy trips gain credits, and those who don't have to purchase credits, and a price will be revealed. But we can also, some studies are looking at explicit charges, and we basically, two studies, ours and the other one, show that for like a 10% increase in road use cost, you can get a 5 to 10% reduction in VMT. So summary. Automation is highly valuable. This is a really important point to me. I spent a lot of my career looking at hydrogen vehicles and biofuels and electric vehicles. All great technologies, all hard to get into the market. Automation has some technological barriers, but it has huge private and commercial value. And so it's very likely to go forward because of its time, safety, convenience, and cost advantages. So we need to think carefully about what to do. And it can have significant vehicle miles traveled effects and energy use effects, as we described, from induced demand and unoccupied travel. If shared mobility is going to help, it needs to change dramatically. Maybe we'll get a global optimization of the system, but that's not the usual way we do things in our cities. Allocate, let a single provider determine the entire vehicle network, fueling network, and schedule all the rides. So in fact, if we actually have a competitive system, we will continue to see, if it's profitable, we'll continue to see essentially over-provision of the services and congestion and all of the other associated problems. So widespread electrification can make a difference, and it has some advantages in this space, but its success is not assured. And finally, cost, incentives, and policy matter. Interesting areas are really in the city domain: roadway access, curb access, road use charges, and occupancy incentives for shared mobility. Those are potentially regional or state-level initiatives that could make a big difference. Thanks so much for listening, and I welcome any comments later. There's names. Okay.
we have lots of people lined up for questions. We have lots of people lined up for questions, but I want to ask Lou one question before I turn it over to the audience, and that is, could you talk a little about heavy-duty trucks and the challenges in electrifying them, and some of the novel ideas being bandied about, like the electricity and road sort of solutions?
Okay. Yeah, I know you're into that. We've talked about it. As I showed, I think for let's say over-the-road long-haul trucking, fuel cells are a pretty interesting option. Those trucks are actually probably no heavier than diesel, and whereas battery electrics would be very, very heavy and lose payload, and you have range advantages. But as I also showed, there's a lot of barriers to getting fuel cells in there. But people are looking at other things like catenary electric trucking or in-road inductive charging. And we have done a comparison of those things, and if you went big, if you had big systems, the costs, especially catenaries, I think, aren't really too bad. They're not much different than battery electrics, and maybe even inductive road charging, if you can get some of the costs down, could look good. But they also have these huge chicken or egg problems. You've got to, all these things ultimately mean at a highway level, you've got to decide as a society what you're going to do. It's kind of hard to be technology neutral on this. So anyway, yeah, there are many options, and we haven't gotten very far with any of them.
Okay. Thank you. Andrew.
Yes, great presentations. I'm Andrew Slaughter with Deloitte. Suppose we have good penetration of automated vehicles operated by rideshare services. Do they compete with driver-owned passenger vehicles, or do they compete with mass transit systems? How does that work?
I think the answer to that is both. I think it's it's no accident that by far the biggest market for TNCs are cities with robust public transportation networks, because it's not driving alone in your own personal vehicle is not a mode that cooperates with other modes. Individuals either fall into the modal usage pattern where they always use their private vehicle, or they are open to other options. And usually people who use active modes or transit tend to stitch together a bunch of different modalities. So I see in the short to medium term TNCs offering, being another mode that seeks to compete with the hegemony of private vehicle ownership. I think in the long term, we have to think about what public transport, and that's in the short to medium term. I think in the long term, right, I think when people talk about public transportation, they tend to think of buses and trains, which are specific form factors. And I think especially trains and buses on arterial routes will still continue to have a very compelling application in fighting back congestion. Automating a vehicle doesn't increase by that much the amount of vehicles you can fit on the road. You can't get millions of people into Manhattan on individual vehicles, no matter whether they're autonomous or not. So I think there's still going to continue to be a role, but perhaps there is a broader range of modes. Right now, public transportation is mostly trains and 40 to 60 passenger buses, but maybe there's a broader range of what it means to be public transportation. Maybe there's an emergence of some intermediate sized vehicles that are more appropriately sized to the specific system at hand.
Can I give a very brief?
Sure.
Oh, yes, please.
That's great. So that question, Andrew, is often expressed as whether automated and shared vehicles are a substitute or a complement for transit. And that's an active area of research. Regina Clulo is one author who, with a couple other people, wrote a study showing that initial results were that the principal rides substituted for walking.
UC Davis study.
Yes, formerly, yes. All right. Substituted for walking, trips that would not have been taken, or transit, not cars.
Yes, sir.
I'm interested about the refunding back in transportation, because in the presentation we see that with reduced the cost, there will be an increased demand. And with more demand, there will be more congestions, and they may reduce the benefit we see for the reduced time and other values. If we consider that feedback in the model,
Yes.
expect less benefit than we see for the transport vehicles and
Paul?
Yes, that feedback is being considered. It's a very important one. There's another interesting feature of automated vehicles. They both make the rider more tolerant to congestion. The famous picture of a Tesla vehicle driver sleeping on, 287 outside of. They make the rider more tolerant to congestion, but they also, when coordinated, can reduce congestion. So it's quite complex.
I think great answer. I think in the value of time studies, we do have an understanding of how the passenger values their time and how versus how the driver values their time, because there's less of a cost of being a passenger. Although interestingly, the cost of being a passenger varies with congestion. People would rather not be a passenger in congested conditions. But I think what the driving factor is going to be how autonomy interacts with the built environment. If they are used to mostly serve on-demand rides in cities, I think you could see a greater rise in dense walkable land use, which could counteract it, whereas the possibility of significant congestion could act as a damper on the potential application of AVs to serving rural and suburban and exurban commuters. I think that this implies that maybe there's a dampening on the potential ceiling on how much you could shift to AVs in that modality.
Jim?
Yes, this is mostly directed to Paul. I really appreciate you're looking very carefully at the VMT effects, because I think that's going to be very much a biggie. And I wonder, could you comment on your thoughts about the degree to which either automation alone or automation with mobility as a service will cause shifts in the structure of cities, where people live, where their willingness to commute long distance if they can not be tied up in it, but they can be playing video games on the way in or doing something productive. The tests that we've had that I've seen are basically short term, so nobody changed where they live. But could you talk a little bit about this effect on where people choose to live vis-a-vis urban centers and their work? Thanks.
Sure, thanks, Jim, and that's a really important question. So the Smart Mobility Initiative is now attempting to couple these actually relatively short-run, even hourly models of cities with spatial development models like Urban Sim, and to address this question. And so it's not my subject expertise, but I do know these models, for example, make locational decisions based on transportation costs to essential centers, and so they would respond to that, and presumably if well benchmarked to historical behavior, they would capture that type of thing. So it's, the accessibility of any amenity is always a critical determinant of property values and locational decisions. This has to be important in the long run, and we have a lot to learn.
Yes.
Yeah, my talk wasn't on that, but I've certainly been thinking about that and have done some work in that area, but not specifically on what happens in terms of a kind of a rebound. I mean, there's a lot of rebounds in play here, which include people possibly living farther away because they don't have as much of a time cost when they're traveling, and also, as got mentioned somewhere along the line, Americans do keep moving to larger vehicles, and the whole world is moving to larger vehicles. And so my personal, I don't know if it's a hell or a heaven scenario, but it's that everyone no longer owns a house. They just own a really large RV. They ride around all the time, and occasionally it pulls up next to some office if they need to go in. And yeah, they're watching video games and movies, and maybe they have a hot tub in there. And so everything's different in that world. But I don't think it's good for energy.
So